Myself, Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today, in the lecture series of Microwave and Radar Engineering, I am going to deliver before you Power in Rectangular Waveguide. Now, the power transmission in a rectangular waveguide. The power transmitted through a waveguide and the power loss in the waveguide walls can be calculated by means of a Pointing theorem. As all of you are aware with the term of Pointing theorem, in the Pointing theorem we used the Pointing theorem for calculation of power transmitted, and it depends upon the electric field and magnetic field propagating. So, for using the Pointing theorem for the calculation of power, we have to gather the knowledge about the electric and magnetic field, and already we have calculated the electric field and the magnetic field components in a rectangular waveguide for both transverse electric, that is TE, and transverse magnetic, that is TM or TM mode. So, already we have this component. So, when we have this component, then it is very much easy for us for the calculation of power. For the calculation of electric and magnetic field, if you want to go through, please refer the previous classes videos. It is assumed that the guide is terminated in such a way that there is no reflection from the receiving end. That means in this particular calculation, we are assuming that there should be no reflection from the receiving end. That means there should be no existence of the standing wave and there should be no loss. The how much signal we are transmitting is given to the system is being transmitted. No signal is get reflected. So, this is the assumption. Or the guide is infinitely long compared with the wavelength, and either we should assume that there should be no reflection, or we assume that the guide length is infinitely long as compared to the wavelength. With this is the condition, this is the requirement for making the system lossless. So, either we should terminate the guide in such a way that should be no reflection, or we should take a waveguide having a very long as compared to the wavelength. So, we can take either of these two for the calculation of power transmission in a rectangular waveguide. Now, apply the Pointing theorem. So, when we apply the Pointing theorem, what is the Pointing theorem? The power transmitted through a guide is given by PTR, that is the power transmitted should be a closed loop integration of P into ds. ds should be the surface area. P is calculated E into conjugate of H. Asterisk sign basically denotes the conjugate, and a half denotes the average power transmitted, and ds the surface area. So, this is the power transmitted through a guide. Now, for a lossless dielectric, the average power flow through a rectangular waveguide is given by what we have done here. But basically what we have 1 by 2 integration of E cross H conjugate ds. And we know that E upon H should be equal to the intrinsic impedance. And if we want to continue with the different components of the electric and magnetic field, so impedance should be equal to Ex upon Hy, and for the another expression minus Ey upon Hx. In general, we can say that it is equal to E upon H. So, what we have done, if we want to replace this H with the help of E, so what we will do? We will have H is equal to Z E upon ZZ. So, that thing we have done here. We have So, when we replace this half in the place of E as it is and in the place of Z, E upon ZZ and ds, the area, surface area, this is represented by dA. So, what we will have? E square dA and ZZ is the constant. So, it is here. So, we will get this expression of power transmitted in the terms of electric field. And if we want to have that in the terms of magnetic field, we have to same E by H is equal to ZZ. So, E in the terms of H, ZZ H. So, when we replace it, half E ZZ H cross H conjugate and ds, area dA. So, what we are getting? 1 by ZZ by 2 H square dA. So, we can have the expression of power transmitted both in the terms of H and E, where this E should be the E is x square plus E y square and H square should be equal to H x square plus H y square. And now, we will move towards the T and the TM mode. So, for that what we are doing actually? We have already calculated the intrinsic impedance value in the for the T and TM mode. So, just we are substituting this value for both the T and the TM mode. So, for calculating the TE mode, average power transmitted through a rectangular waveguide, we are replacing ZZ of the TE, that is equal to this one. Got it? And nothing else. And since dA should be the x and y, the area of a rectangular waveguide A, B, that means in the x direction and in the y direction. So, the complete area this one. So, dx dy limit kya? Limit is 0 to A and 0 to B. So, we are just doing this and E in the expanded form. So, this is the average power transmitted through a rectangular waveguide for the TMN mode. Now, TMN mode, same thing, we have replaced ZZ, which are having in the expression with the TM mode. So, this is the ZZ expression for the TM mode and everything remains the same. Area of a rectangular waveguide, dx upon t limit is 0 to B and 0 to A, and this symbol is intrinsic impedance and this is given by under root mu upon epsilon. So, this is the expression for the transmitted wave for the rectangular waveguide and then with the T mode and the TM mode. Now, power losses in the rectangular waveguide. So, the main reason of power losses in the waveguide is the dielectric present in the waveguide and the losses in the guide walls. So, we will deal with these two reasons for the losses in the rectangular waveguide one by one. So, power losses caused by the dielectric attenuation. In a low loss dielectric, what is the condition for a low loss dielectric? That is sigma should be very less than the mu epsilon. So, always consider if somewhere it is asked what is the low loss dielectric, that sigma should be very less than mu sigma. The propagation constant for a plane wave travelling in an unbounded lossy dielectric is given by alpha and this is equal to sigma by 2 under root mu by epsilon. Already we have seen that alpha by 2 as it is and mu by sigma is our intrinsic impedance. So, we are going to replace this with the intrinsic impedance expression. The attenuation caused by the low loss dielectric in a rectangular waveguide for the T and the TM mode now. So, for the T mode, what is the sigma by 2 and the expression this one for the T mode and for the TM mode. So, what we are doing basically, we are replacing the impedance expression for the TE and the TM mode in this expression. for getting the TE mode and the TM mode, as we have done for the calculation of power transmitted. The same thing we have done for the power transmitted for the TE and the TM mode, and the same thing we are doing for the calculation of the attenuation. As f is greater than the very greater than fc, the attenuation constant in the guide approaches for the unbounded dielectric. So, this is the condition. If we have f, what is f here? This. If f is very greater than fc, what will happen? If f is very greater than fc, then this expression will be a very small value. Then in that case, alpha g should be equal to sigma intrinsic impedance 2, this will be 1, and fc upon f is very small, then this can be considered as a 0. So, we have sigma n upon 2. This is same as for the unbounded medium, unbounded dielectric. So, that is written here that as f is very greater than fc, the attenuation constant in the guide approaches for the unbounded dielectric. This is a simple meaning of, you can have this from the mathematical expression also. If the operating frequency is very below the cutoff frequency, the reverse condition, the attenuation constant becomes very large and non-propagation occurs. But if this condition does not exist and the reverse of this is happening, then in that case our attenuation constant, which is this one, fc, what is written here? Fc is very greater. Then this case, this attenuation constant value become very large, and if the attenuation increases, that means our wave will definitely start propagating, because attenuation will always leads to the loss of the signal from the any wave. So, attenuation constant become very large, so non-propagation occurs. So, if we want the wave to be propagated in a particular medium, the operating frequency has to be greater than the cutoff frequency. Do not take that frequency in which the operating frequency is below the cutoff frequency if we want the wave to be propagating. Now, power losses by the guide wall. Power, when the electric and magnetic field intensity propagate through a lossy waveguide, their magnitude can be written as this at the z equal to 0, and if the wave continues to propagate in the z direction with the attenuation constant alpha g, this is the expression of the electric and the magnetic field property propagation. E should be equal to E naught z e to the power minus, that means it is decreasing. If it is E or naught z will be the maximum one which occurs at z equal to 0, and if we keep on increasing z, that means z equal to 2, whatever be the unit, and that means any value which we are getting, for example, if we are getting E naught z, this should always be less than E naught z. Okay. And similar for case for the magnetic field also, e to the power minus alpha g z, and with what proportion it is decreasing? Alpha g. For a low loss guide, the time average power loss decreases exponentially with the e to the power minus 2 alpha g z, and for that condition power transmitted should be equal to power transmitted e to the power minus 2 alpha g z plus power loss e to the power minus 2 alpha g z. And for condition when P loss is very less than the PTR, that is power transmitted, in that case of course attenuation constant should be very less than 1. Only that in that case transmitted is possible where attenuation constant is the lower side. If the attenuation constant is at the higher side, the reverse condition will happen, that is power loss should be greater than the power transmitted. So, the main factor which is contributing to all this is the alpha g. So, From that we are getting P loss upon PTR plus 1 plus 2 alpha z z. So, what we are having from here? Alpha g should be equal to P loss upon PTR 2 and z. So, P loss upon z, P loss upon z equal to PT 2 PTR, and this P loss upon z is our PL. So, when we say that what is the PL, the PL is the power loss per unit length, and we have that from there, power loss upon z, and the z is the length along which the wave is propagating. So, the PL is equal to power loss per unit length. Now, consequently, the attenuation constant of the guide wall is equal to the ratio of power loss per unit length to twice the power transmitted through the loss. So, this is the just the attenuation constant is equal to the power loss per unit length upon the 2 into power transmitted, and the same is written here. The attenuation constant of the guide wall is equal to the ratio of power loss per unit length, which is our PL, to the twice, that is 2, to the power transmitted, that is PTR ratio. The power loss per unit length of the guide is obtained. How? The power loss per unit length is obtained by integrating the power density over the surface of the conductor. We are integrating the power density along the surface resistance, that is the surface resistance of the guide. This is the value formula for the calculating of power loss per unit length, and here the two terms arises, RS, that is surface resistance, and HT, that is the. So, the surface resistance is given by rho upon del, and this is equal to rho is the resistivity of the conducting wall, and inverse of this will be the conductivity 1 by sigma del, and now we replace the value of del, that is our skin depth of the penetration in the medium. The skin depth is basically the distance up till which any wave can penetrate, and it is equal to the 1 upon under root of pi f mu. So, in the place of del we are writing under 1 by under root of pi f mu, and the sigma remains the same. Now, HT, the another expression which comes in the power loss per unit length, the HT is the tangential component of the magnetic field intensity at the guide wall. Now, when we substitute the value of PTR and PL in the equation of alpha g, we have already have the value of PTR, that is this one in the terms of electric field, and in this one in the terms of magnetic field, and now we have the value of PL, RS upon 2 integration over the surface HT square ds. So, when we substitute this value into the alpha g, that is our attenuation constant is equal to this formula. We have already calculated this. So, just substitute the value and you will get this one, PL values and the PTR value, you will able to get this, and H is equal to Hz Hy square, and Ht is equal to the Htx component square plus the magnitude of the Hty square. So, I think all of you are able to do this, and this is a derivation. Without doing the derivation part or solving, you can't able to do it on your examination. So, always try to do this. Now, one numerical related to this. An air-filled waveguide with a cross section of 2 cross 1 centimeter. Always consider this as the A and this is the B. A should be greater than the B for the any rectangular waveguide. Transport energy in the TE10 mode. If you remember, TE10 mode is the dominant mode which exists in a rectangular waveguide at a rate of 0.5 HP. The impressed frequency is given as 30 gigahertz, and you have to calculate the pick value of the electric field occurring in the guide. So, before proceeding toward this numerical, what we have to do? Basically, this is the for any question in which we are required to have the power. So, we have to start with the pointing theorem. So, for calculation of the power using the pointing theorem, what the first thing which we required? We basically required the electric field and the magnetic field component. So, we have to find out the first thing which we have to do, we have to find out the electric field and the magnetic field component for the TE10 mode in a rectangular waveguide. So, already we have gone through this derivation part and we have obtained the field component of the TE mode. So, this is the expression for the different field components of the TE mode, and if we want to find out the field component of the dominant mode, that is TE10 mode, that is required in our numerical, what thing which we have to do? The expression is always in the form of TMN, that means Mn, M is equal to 1 here and N is equal to 0 here. So, one by one, what thing which we have to do? We have to substitute each of the expression where M is written by 1 and N where N is written by 0. You have this expression in every term, got it? So, when we substitute this value M equal to 1 and N equal to 0, we are able to get the field component of the dominant mode, that is TE10, and we have this one. So, all of you just solve it by substituting the value of M and N. In examination, I have solved it for the TE10, but in many examination you are asked to solve for the TM10, 01. This is a very general questions which comes in the examination. So, try to do this. Now, this is the expression of the electric and the magnetic field for the TE10 mode. Now, we are able to get Ex, Ey and Hx and then the Hz values, these are the. Now, and Zz, you know, this is equal to this one omega mu naught upon beta g Zz, which is required in this numerical. Now, for calculating the further for calculation, what thing which we are required? We are able to require the propagation phase constant, that is the beta g, and the beta g for calculation is done omega square mu naught epsilon naught minus pi square a square. We know that this C is equal to under root 1 by mu naught epsilon naught. So, what we have done, so and omega is equal to 2 pi f. So, for the omega, this expression what we have done, we have replaced the omega with the 2 pi f. So, pi we can take outside. So, this pi square will be pi here and 2f square, and this will be under root mu naught epsilon naught is equal to C. So, this is on the numerator side. So, C is comes on the denominator side because it is the inverse relationship, and since is equal to mu naught epsilon naught, so C will be C square here, and since we have taken the pi square outside the under root, so this will remain pi and we have 1 by a square. Now, you have the value of f here, that is equal to, and you have the value of so 1 by 1 we have 30 gigahertz, we have here 30 gigahertz frequency. So, 30 yani 3 square, when we take the f square it will be 9 into 10 to the power 10, and we know that C is equal to 3 into 10 to the power of 8, but when we take the square of it, it will be 9 into 10 to the power of 16, a 2 into 2 centimeter, that is the square of this, we will get the beta g expression. Now, power delivered, we have taken the power delivered, P is equal to this expression half limit 0 to b, 0 to a, e cross h, dx dy uz. And when we put the expression of E and H here, we have already derived the expression for E and H, that is what we will take here, Ey and Hx. So, we substitute the value and after solving we will get this one, and the total what is having, we have 0.5 HP, we have converted that into the power and substituted the value of beta g, already calculated omega mu naught, A and B, we have get the field intensity expression. So, every one of you solve this numerical is very important also because this is the numerical based on the power transmitted on the rectangular waveguide. Thank you.